So let's look at all these reactions together. So right now we know that we have four different reactions: SN1, SN2, E1, and E2. And the primary question is, if I give you an example, what reaction's occurring? And with this, the first question that you always ask is, what kind of halogen do I have? That is the primary deciding factor in these reactions. And the question of what reaction's going on, the primary question is, what kind of leaving group do I have? And then after that, there's some other questions that'll occur, and we're going to run through these. So here's a sheet. This is a nice flow chart. I will send it out to you guys. But the first question you asked is, what kind of leaving group do you have? And then depending on what kind of leaving group, and by leaving group I mean halogen, there's a couple other questions that you have that will lead you into this, to the right answer. So let's take a look at these individually. And then always remember that once I figure out what reaction's occurring, I say, is there something I need to add to it? So remember, SN2 reactions have an inversion of stereochemistry. SN1 forms a racemic mixture, or we lose stereochemical control. And then both for E1 and E2, the hydrogen in the leaving group must be adjacent, and Zaitchev's rule is in effect. So the question is what reaction's occurring? And the main thing that is involved in this is the sterics around my electrophilic carbon. Is my electrophilic carbon, or my leaving group, or my halogen, however you want to look at it, primary, secondary, or tertiary? And then we're going to find that after we ask that question, we might have to follow up that question with looking at the nucleophile itself. So the nucleophile has a secondary importance. So sometimes we need to say, okay, what kind of nucleophile do we have to determine my product? But really the first thing we look at is, what kind of leaving group do we have? So the first leaving group is a methyl leaving group, and it's not on my sheet because this is the easiest one. Methyl means that I have a halogen attached to a CH3, so there's not a lot of variation in here. This species can only go SN2 reactions, and so this is important because it has so little sterics. It favors SN2 reactions so much, that's all that can occur. And you can see, well, you can't have elimination reactions because you need at least two carbons to form a double bond, but methyl carbocations are so unstable, I can't do an SN1 reaction. So with methyl halogens, I always get an SN2 reaction. It doesn't matter what I react with. It doesn't matter if my nucleophile is a good nucleophile or a poor nucleophile, it's going to react in an SN2 reaction. So here, when I look at this, if this is one of my a reaction, and I say draw the products of this reaction, first thing I do is say, what kind of halogen do I have? So the carbon that's directly attached to my halogen, there are no other carbons attached to it, CH3. I know this is going to be an SN2 reaction, but in terms of this, I know it's a substitution reaction. So my thinking is going to be different. Am I doing a substitution reaction, or am I doing a elimination reaction? Here I'm doing a substitution reaction. With a substitution reaction, what you do is you kick out the leaving group, you connect my nucleophilic atom, these lone pair electrons, and my electrophilic carbon. So I'm going to be removing this carbon-bromine bond that kicks off. I'm going to be connecting my oxygen and my carbon. And then remember, neutral nucleophiles lose a hydrogen. So this is water, it's a neutral nucleophile. So I'm going to be losing one of these hydrogens. So what's going to be coming off my carbon in my product is an oxygen and another hydrogen. So here now, when I react water with a methyl hydrogen, what I end up forming is an alcohol. So this carbon's there, this carbon's there. This is my nucleophile. I connect the nucleophile with my electrophilic carbon. Neutral nucleophiles lose a hydrogen. So instead of H2O, what I have is OH. If I ask follow-up questions, this follows an SN2 mechanism. And this is regardless of the fact that this is a poor nucleophile. So yeah, good nucleophiles tend to favor SN2 reactions, that's true, but because this is has so little steric hindrance, it doesn't matter that this is a poor nucleophile. It's still going to undergo an SN2 reaction. So don't worry about the product solvents part. We'll might talk about that later. Okay, so we have a primary leaving group. So by that, or primary halogen, by that I mean the carbon that's directly attached to my halogen only has one other alkyl group attached to it. So here we have still have very little steric hindrance, and so what we're going to get is an SN2 reaction almost every time. So with every other nucleophile except one, so this is one very important exception, every other nucleophile, doesn't matter if it's a good nucleophile or a poor nucleophile, I'm going to be doing an SN2 reaction. There's one exception to this rule, and it's that sterically hindered or big bulky base. And I mentioned this to you earlier, and we're going to take another look at it. But remember, SN2 reactions do not like sterics. And say I want to get an elimination reaction with my primary leaving group, there's not enough sterics to stop my SN2 reaction. So what we're going to do is artificially put sterics into my reaction to allow for an E2 reaction to occur. So the idea is, if I want to do an SN2 reaction with a primary leaving group, I don't have to do anything. It will already do that. But say I want to get an elimination reaction. I want to form the double bond. What I need to do is use a specific reagent that puts sterics into this reaction artificially. So this is called a big bulky base, and the base is called potassium T-butoxide. Sometimes it's written TBUO minus K plus. There's a few different ways of drawing it. T-butanol is probably the solvent, but this is T-butoxide. This is my big bulky base, and the idea is this base is very sterically hindered. And so when I use a primary leaving group, when I use this base, it's going to put sterics into my reaction such that I can get an E2 reaction. So normally with primary halogens, there's so little sterics, my reaction tends to go SN2 unless I use my big bulky base. The big bulky base puts sterics into the reaction. This allows my reaction to go E2. So, and then also with this, notice when primary halogens form primary carbocations, so we don't get any SN1 and E1 products. It's not possible. So this is the idea. Once I figure out I have a primary halogen, the only question I have is, am I using my big bulky base? Am I using T-butoxide? If the answer is yes, okay, I get an E2 reaction. If the answer is no, I get an SN2 reaction. Notice it doesn't matter what kind of nucleophile I have. It's going to be SN2. And so this is probably, well, let's take a look at it. But this is one of the most common mistakes people make on this reaction is they try to use the big bulky base as a nucleophile. That's not what it does. It acts as a base. So let's take a look at this. So here's one reaction. I say, what's the products and what's reactions going on? The first thing I look is my leaving group. The carbon that's directly attached to the halogen is attached to one other carbon that makes it primary. And then when I want to know what reaction is going on for a primary halogen, I only ask one question. Is the thing attacking it a big bulky base? No, this is not T-butoxide. So this is undergoing a substitution reaction. So my brain goes into substitution mode. I say, what happens during a substitution reaction? Okay, literally during a substitution reaction, my halogen gets replaced by my nucleophile. So I kick out the halogen, bromine's gone. I connect my nucleophile to my electrophilic carbon, this one, and we lose the negative charge during it. So this is a negatively charged nucleophile. I don't have to change the number of hydrogens. So I kick out my leaving group and replace it with OH. So because this was not T-butoxide, I know this is an SN2 reaction. So when I look at this one, so same molecule, it's still my primary leaving group, but now I'm reacting it with T-butoxide. And so you can kind of see this. It would be very hard for this oxygen to come in and attack this electrophilic carbon. It would be much easier for it to grab one of these adjacent hydrogens. So this would rather act as a base than a nucleophile. So this allows for the E2 reaction. So I say primary leaving group, is it reacted with a big bulky base, T-butoxide? Yes. This means it's going to be an E2 reaction. So I go into E2 mode. I say, okay, I better form a double bond during this. I find my electrophilic carbon. I find adjacent carbons with hydrogen. I then say I kick off my leaving group. I kick off an adjacent hydrogen. I form a double bond across there. So here, when I look at this, this is my product. So this carbon is this one. So I undergo an E2 elimination because I was reacting it with T-butoxide, my big bulky base. Okay, secondary leaving groups are by far the toughest. The reason why is they're kind of in the middle in terms of sterics. They are not really sterically hindered, and they're not, you know, less steric hindrance. So the idea is there's the possibility of all four reactions occurring depending on what type of nucleophile I have. So this is where it gets a little tricky. So in the exam, you get a question and I say, what's the product of this reaction or what reaction's going on? You see a secondary leaving group, you need to take a second because this is the trickiest one. And so there's some sub questions that we need to ask. So here, secondary, my leaving group, the carbon attached to my leaving group is attached to two other carbons. I need to ask some more questions. The sterics doesn't tell me what reaction's going on. So the idea is, with good nucleophiles that are not strong bases, I get SN2 reactions. So of the nucleophiles I talked about, there's the carboxylate, cyanide anion, and the hydrosulfide anion. So these are the nucleophiles that we talked about that are good nucleophiles. So I didn't draw them in, but they have lone pair electrons and a negative charge. They are good nucleophiles that are not strong bases. If I have a good nucleophile that are strong bases, like our alkoxide or hydroxide, I get an E2 reaction. And so we already talked about this. When we have these nucleophiles, does the nucleophile want to act as, or does my nucleophile slash, base want to act as a nucleophile, or does it want to act as a base? Well, if it's not a strong base, it wants to act as a nucleophile. And these are the three nucleophiles that do not act as a strong base, so they would rather act as a nucleophile. Alkoxides and hydroxides are good nucleophiles, but they're also strong bases. For secondary halogens, they would rather act as a base and undergo an E2 reaction. So if I have neither of these, if I have some kind of weak nucleophile, which are also weak bases, I get the SN1 and E1 tied together. So remember, if I get one, I get the other one. So weak nucleophiles, remember we talked about this earlier, are like water and alcohols. So they have lone pair electrons, but no negative charge. And for the sake of argument, I believe this is generally true. Between those two, SN1 and E1, they're always tied together. So if I get one, I'm going to get the other one. But the SN1 reaction tends to be the major product. So when I look at secondary halogens, the first question that I have, so after I determine I'm dealing with a secondary halogen, I say, am I using a good nucleophile or a poor nucleophile? Do I have lone pair electrons and a negative charge, or do I just have lone pair electrons? If I have a poor nucleophile, just lone pair electrons, I get the SN1 and E1 tied together. If I have a good nucleophile, lone pair electrons and a negative charge, I need more information. Is my good nucleophile a strong base or a weak base? Well, if it's a strong base, it would rather act as a base. Despite the fact that it's a good nucleophile, it would rather act as a strong base. It's going to undergo the E2 reaction. If it's a weak base, it would rather act as a nucleophile. I get the SN2 reaction. So you can see, depending on the type of nucleophile that I'm using, I can get E2, SN2, or the SN1, E1 combination. So this is where it gets a little tricky. So let's take a look at some of these reactions. I say, what's going to be my product? What reaction's going on? Still, the first thing I look at, what kind of halogen do I have? Carbon directly attached to my halogen is attached to 2 other carbons. This makes it secondary. So this means I got to look at my nucleophile to understand what's going on. My first question is this a good nucleophile or a poor nucleophile? So lone pair electrons, negative charge. It's a good nucleophile. Then I say, is it a strong base or a weak base? So the only strong bases we had that we talked about, strong base good nucleophiles, are hydroxide and alkoxide. If it's not one of them, it is a good nucleophile that's a weak base. So because this is a good nucleophile that's a weak base, it would rather act as a nucleophile. So we get an SN2 reaction. I then go into SN2 mode. I say, what happens? Substitutions. I replace the leaving group with my nucleophile. I kick off the leaving group. My nucleophile connects to the electrophilic carbon, and we lose my negative charge. So instead of a bromine, there's going to be a a C triple bond N coming off of there. And notice, this is why we focus in on the electrophilic carbon. Everything else is just stuff that doesn't really matter. The electrophilic carbon is where all the action's at. That's where we focus to, and it doesn't really matter if there's 2 carbons or 5 carbons coming off of here. All I end up doing is replacing the replacing the halogen with my nucleophile. So when I look at my product here, what I see is, yeah, I kicked off my leaving group and I replaced it with my nucleophile. It's that simple. Everything else comes along for the ride. I just say, okay, well, my electrophile is also, my electrophilic carbon is also attached to a CH3, CH3, and an H. And so in my product, CH3, CH3, and an H. That's not part of the reaction. The reaction is kicking out the leaving group and replacing it with my nucleophile. So this occurred because my nucleophile was a good nucleophile, lone pair electrons, negative charge, and it was also a weak base. So the reaction was SN2. When I look at this one, so still a secondary halogen, I go through and I say, first question is this a good nucleophile? So this is methoxide, definitely a good nucleophile, lone pair electrons and a negative charge. Then I say, is it a good base or a weak base? Or I mean, excuse me, a strong base or a weak base? So alkoxides and hydroxides are our good nucleophile, strong base. So between these two, because this is a secondary halogen, between acting as a nucleophile or acting as a base, with a secondary halogen, alkoxide would rather act as a base. So this is going to be an E2 reaction. Then I go into E2 mode. I say what's happening here. I kick off the leaving group. I kick off an adjacent hydrogen. So this carbon's going to go from H3 to H2. I draw a double bond across here. This is going to be an E2 reaction. How I knew this? Secondary halogen, the species it's reacting with is a good nucleophile that's a strong base. So it would rather act as a base and remove a hydrogen, causing an E2 reaction. So here, this carbon is this one. This carbon is the original electrophilic carbon, is this one. And I say, what's coming off of there? A hydrogen and a CH3. Hydrogen and a CH3. So let's do one more. Same thing, secondary halogen, but now I have a poor nucleophile. So methanol and water, or alcohols in general, are poor nucleophiles. So with a secondary halogen, this molecule can't go in and attack. It's not a good nucleophile. It's not a strong base. It can't go in and attack the electrophilic carbon. It can't go in and remove a hydrogen. It has to wait around until the leaving group pops off. So what we end up forming is the SN1E1 mixture. So because this forms the carbocation, we end up making a mixture of both. So for the substitution version of it, the SN1, we kick off the leaving group, we connect the nucleophile and the electrophilic carbon, and neutral nucleophiles lose a hydrogen. So what's going to be coming off my electrophilic carbon is OCH3. So that's going to be the SN1 version. And then likewise with the E1 version, we kick off the leaving group, an adjacent hydrogen, and then draw a double bond across there. So this was because we're dealing with a secondary halogen, and the species it's reacting with is a poor nucleophile. It's also a weak base. We end up making the E1 and SN1 products together. So with the tertiary halogen, we're back on the other side. Now we have very sterically hindered halogens, and also it's very favorable for doing the SN1 and E1 reactions together, because when we kick off this halogen, what we end up doing is forming relatively the most stable carbocation. So with this, what we end up forming still kind of depends on the type of nucleophile we have, but we will usually only have two major parts. So the only reactions that are possible with the tertiary halogen is either E2 or the SN1 E1 mix. And we tend not to confuse the two. Either we want one or want the other one. If I want the SN1 E1 mixture together, what I use is our weak nucleophiles that are also a weak base. So that's our alcohols and water. So between these two, if we get one, we get the other one. And remember, the SN1 reaction is considered the major product. But if I want to get an E2 reaction with a tertiary halogen, what I want to use is a strong base nucleophile. So those are our alkoxides and our hydroxides. And remember, I can get an E2 reaction because E2 reactions are not affected by sterics. SN2 reactions are affected by sterics. So with a tertiary halogen, I can't get SN2 reactions. So when I look at this, once I figure out that I have a tertiary leaving group, my first question is, which one of these two variations do I have? Do I have a poor nucleophile And with a poor nucleophile, what I end up with is the SN1E1 mix, or do I have a good nucleophile that's also a strong base? And if I have that, I get an E2 reaction. So notice I can't get an SN2 reaction at all. So when I look at this one, tertiary halogen, the carbon attached to my halogen is attached to 1, 2, 3 other carbons, tertiary. I look at what it's reacted with, poor nucleophile. So I know I'm going to be ending up making the SN1E1 combination. So substitution, kick out the leaving group, connect the nucleophile and the electrophilic carbon. Neutral nucleophile lose a hydrogen. So what's going to be coming off of this carbon? Oxygen and the CH3. Likewise with the E1 elimination, kick out the leaving group, kick out an adjacent hydrogen, and I draw a double bond across there. So I know this because I'm dealing with a tertiary halogen and a poor nucleophile. The other one is, so once again we have the tertiary halogen, but here I have my good nucleophile / strong base. It can't act as a nucleophile because we're dealing with a tertiary halogen. It's too sterically congested, but it can act as a strong base. So tertiary halogen, my good nucleophile / strong base, it's going to act as a base. I'm going to get an E2 reaction. So same deal, kick off the leaving group, kick off an adjacent hydrogen, I draw a double bond across there, I get my product. I knew this because tertiary halogen, a good nucleophile that's a strong base, because it's a tertiary halogen, its only choice is to act as a strong base and undergo the E2 reaction.